Okay, so what we'll do today is derive finally the dynamics equation and study its properties. So using the Lagrange approach, and we first define the potential energy, which is a function only of the generalized coordinates and not its time derivatives. Okay. And you can then, so we take two components, link and the motors separately, and we find out what is the potential energy. That is very simple, we just find out what is the vertical height and then multiply it by g, and so that term will land up here. So it is no big deal, fairly simple, and you already know how to do forward kinematics. So in terms, writing in terms of q is not a problem. Now here we are writing it in this form, but when you actually compute it, you will plug in numbers for all these terms. Okay, so you will actually plug in numbers. Then you start working on the kinetic energy, and it is a little bit more complicated, but in the end you calculate Jacobians, and in this case we have just split into two parts, the component which is in the axis, along the axis, the angular velocity component and the velocity component. So these are these three vectors which have been split up, and this is the definition of it. And then you can write the kinetic energy of a link in terms of that. So two components, half mv square term, half I omega square term. Then you look at the motor, which is very similar, except that you have to use, instead of position vectors going to the center of mass of the link, you have to go somewhere to the center of mass of the rotor. And then you have to take care of the fact that where k is the step down or step up is the reduction ratio. Then now this angular velocity is of the previous link, then the speed of the rotor shaft is usually related to the angular velocity of the next link, and the relationship is to the reduction ratio. So you have to just take that into account. Okay. So you again derive these partial Jacobians, which has to be stacked. So you go to add them together, and you will get an expression for the kinetic energy. You just patch it all together, and it turns out that when you put it all together, each one contains a term qi dot qj dot, and this can in general be written in this form, q dot t bq q dot, okay, where q is the vector of all the angular velocities. So this is called a quadratic form because q is on both sides of the vector, and that has some nice properties, and you can expand it out. So this is inertia matrix which is symmetric, positive definite, and obviously configuration dependent because all the dh parameters enter the scenario. So we stopped here and we start looking at new material now. So just a background, so I have just put the equation in blue out there, we need to keep this in mind. So now this term consists, it is the kinetic energy minus the potential energy. Potential energy is a function only of q. So when we take the derivative with respect to q dot, this will have no components. Okay. So this equation is going to land up looking like bq into q double dot plus a matrix n which will be a function of both q and q dot. Okay. And why will you get bq q double dot? I will just flick you back. See, b is in this form. So if you do you take a derivative with respect to q dot, you will get a q double dot term. Okay. So the other thing which you must keep in the back of your mind is that when you write the expression for L, it is a function of q dot and actually also of t. That is understanding. That is why you are taking derivative with respect to time also, though you write q and q dot. Now in them you treat q and q dot as independent parameters actually. though q dot is related to q, you cannot have arbitrary q dot and arbitrary q, though at a particular point you can specify it, that I can be at this point q with this value of q dot, but they are related by the fact that q dot is a derivative of q. But you need to treat them as independent derivatives, I mean independent parameters. So partial with respect to one does not automatically mean you start taking partial with respect to other one because it's a related term. So you literally treat them as separate variables. So if you start doing that, then this nq q dot will consist of two terms, right. So you have to do d by dt del q dot of the b term, the q transpose bq term. So that will give you two terms, right. One will be b dot q, because when you do d by dt of, well, you have to do first del upon del q dot, right, and then do a d by dt of it. Now b consists only of q, it does not have q dot terms in it, okay, it is only dependent on the positions. So derivative of b with respect to q dot will give you nothing. But however, when you take the derivative of the q dot in the front and the back, that will give you back, so one of them will give you back 1 and the other one you still remain q dot. So let us look at this. So if I take the derivative of this term with respect to q dot, then this term will, I mean derivative of q dot with respect to q dot is 1, so you will be left with bq q dot. Once we are left with bq q dot and you take d by dt of q dot is 0, because q dot and q are, they are independent parameters. So you get this b dot term, and then you have these two terms which is the d by dq terms. So you have q dot b, this term and then this term. So is that understood? So very subtle and slightly different mathematics, okay, which you are supposed to know. I mean you have done this partials earlier, but this is the physics of it. Remember that q and q dot are independent parameters, that is what I am looping on. And so finally when you calculate it, this is just a compact notation, right, this is a compact notation. Finally when you calculate it, you do it term by term, okay. So that is where the interesting part is. So you can program at that higher level, but finally you have to expand it into term by term expansions. So this is what you do. So finally you break it down into the components of Bij, which is a function of the generalized coordinates, into q double dot j, plus you have this term. Now this term dBij upon q upon dt, you break it up like this, you write it as partial of Bij with respect to q with respect to qk multiplied by qk dot, and then this term I have to sum over all the k's to get this term dBij q upon dt. Is that okay? Any confusion? No, that is quite standard, you expand it in terms of each one of them, and then similarly dt upon del qi will end up being this term, okay. And you have to switch the summation indices to make it, get it back into the same form, which is allowed operation inside summations. We do not have to stick at the same order of doing that. Similarly you write the du upon del qi term, expand it out, get into this form, and so then you will end up with the equations of motion, which is in this form. So Bij q dot j and this summation, and then here, so you have this jiq term coming here, and you have this hij term, and where each hij is given by del Bij upon del qk minus half del Bjk upon del qi. Now this is expansion. I obviously do not expect to remember this in an exam situation. So that is why you have the A4 size sheet of paper, you have books, okay, and you have notes. And the only problem is, if you pick up almost any book except a book which is maybe 30 years old, right, including my notes, though I have tried my level best to clean up all the indices, there is roughly about a 20% probability that there will be errors in the indices. Okay, so don't be surprised. You pick up any book, including my notes. I am not saying this is sacrosanct, the basic method is right, but there will be error here in the indices. So you should verify when you write a program, when you test it out, you will find there are errors, even if probability of there being errors, even if you have done programmed everything according to the algorithm. So do not be surprised that that happens. Okay, so that's why it takes time to, and you have to verify using test cases and things like that. Okay, so you understand the spirit of it. I am not saying that I have got all the indices right. General principle is right, you have to go back and rederive that. So now let us look at little bit at the interpretation of all these terms. So when I was talking about terms like BII, it represents moment of inertia at joint I axis of all the links which are when all the other joints are locked. Okay. So if I have multiple joints which are extending out, so if I lock the inner joint, then that is fixed to the base. So it is almost like I have locked this and I am trying to find out what is the moment of inertia of all this thing about this joint. So then once I have locked this, then I will look at moment of inertia about this joint. So each BII represents that. Okay. And obviously as you change the configuration, you can quite understand that the moment of inertia will change. And remember, we started from local moment of inertia defined about on each link locally, we multiplied it by the rotation matrices and manipulated it so that I get it in global terms. Okay. So when you did your mechanics course, you were doing that completely on a case by case basis because you had 4 links or 2 links, it was planar, so life was easy. In this, since you have multiple things, it becomes more difficult. But you should also understand that this method you can extend to literally any system, whether it is a 4-bar system, it is an 8-bar system, spatial link. So this is generally extensible, these methods. And so the Bij term, it affects for, it is the effect of acceleration of joint I on joint J. Okay, so that has a component in the final talk. Okay. Then you have quadratic velocity terms. I really hate this term centrifugal. Okay. So this Gij q dot square j or q dot j term, square term turns up. Okay. And so this is like a term r omega squared. Okay. It's similar to r omega squared term, and so there is j, there are 2 j's here and 1 I here. Okay. So there are 2, so acceleration of so this is the force at joint I by velocity of joint j, by the angular velocity of joint j, and h triple I is equal to 0 because del b, I mean II upon del qi is equal to 0. So there is no change in the in a local frame, the moment of inertia does not change because all my links are rigid. Okay, so there is no change locally. If my links are not rigid, then this term will not be equal to 0, but at least in this course we do not deal with it. In fact, in no course in the IIT we deal with it. This is mostly a research topic, what happens and the implications of that. So Gi is a moment at joint I axis of the manipulated in the current configuration by the presence of gravity, and so the whole idea is that when you design the structure, you are trying to make something so that as many of these coefficients Bij and Hij, you should make it ideally 0, or you make it as close to 0 as possible or small or invariant, so that all these coupling terms go away. The more you can make, the more compact your dynamics will be and your life will become easier. So that is the aim. So the art of designing a robot is not to decide ki the link is here and you power the motor, or to paint it orange or yellow or red. It's essentially going back deep in down and basically messing around with these terms, trying to figure out what gives you a most convenient form. And the major groups that you see of manipulators, in which over the last 30 years, or rather in between, say between 1970 to 1990, when dynamics or this kind of dynamics evolved, people have already done that. So when you look at a manipulator configuration, it is primarily because firstly the forward inverse kinematics is very easy, and the second thing is, next step after that is that they try to make sure that as many of these terms are either 0 or constant or very small, so small that you can ignore it from the dynamics equation. Okay, so, and obviously in this course I can't go into the details and teach you how to do that, but it is doable, and you are reasonably, if you are reasonably supple mind, you will understand once you look at the expansions as to how to do that. So what I have not talked about so far is, when I looked at this equation, so I had this zeta sitting on the side, which I said is the, so I looked at the left hand side, I did not look at zeta. So this is the non-conservative forces. So they are the torques at the actuator, there is viscous friction which is dependent on q dot by definition, by speed. Then there is static friction which can be dependent on q as well as q dot, it is a combination, and especially because, but you can simplify it where it becomes Coulomb friction. Okay. In Coulomb friction, it is only dependent on the sign of q dot. So it is not, is dependent only on the sign of q dot. So that is what I am writing here, and this Fs will be a vector of loads which is there, which can be calculated, okay, based on other parameters. So this is a form of that, and then in the last part we already looked at is that if your end effector is pushing or pulling at something, and if you know that vector of push pull forces where the end effector is acting on it, I am pushing and pulling on this, then we already looked at that if you multiply that vector by J transpose Q, then you will get the torques at each vector. Do you remember that? No. When I did infinite small screws, that is what I discussed, that you get that from conservation of energy, because F dot V is equal to power, right. So from, if you look at a static case, there is no, nothing is accelerating, so no power. So if from F dot V you get J transpose Q into HE, the end effector, that vector force has to be equal to 0. So you get this. So finally, so this is the whole set. So BQ q dot C, you get it, well we will discuss C, FV q dot plus Fs sin of q dot plus GQ is equal to tau minus J transpose Q HE. So this is the whole set, okay, nice, compact, simple, alright. So if you are electrical engineer, this is where you start from, okay. If you are mechanical engineer, this is kind of very finish, okay. So the only thing is, what is this C thing? See, what happens now is you want to actually get this in the form where this is q dot, this is q dot, so this is a term of q dot, this is actually a very funny term which is dependent only on the sign, and then this term is q. So essentially you want to write everything as mx double dot plus cx dot plus kx, either equal to a forcing function or equal to 0. So this is this format. So once you can reduce something to this format, the electrical controls group takes over, and they do all their nice stuff on it, you know, the Lyapunov and eigenspace assignment, eigenvector assignment, right, and they can do all other nice things to it and publish nice theses on it, publish nice papers on it, okay. So this is where you land up with, Now, where does this C come from? Now, you actually had an expression which is in this form, Hij_k into Qk dot into Qj dot. It is not very convenient to have it in this form. So, what you do is you say, okay, I want to now write this in this form Cij Q dot j and summation j is equal to 1 to n, so that I have n such equations. Okay. So, you just say I want to write it in this form. So, obviously, C is not unique. There are many functions. So, you can get C in many forms. So, C is not unique, but there is, you can always find at least one Cij which will satisfy this condition. It is very simple, j is equal to 1. So, all you have to do is you have to just sum up Hij_k into Q dot k and then you will get a term for Cij. Okay. But Cij in itself is not unique, you can have several set which will match this, and that takes you to very, very interesting domains. Okay. So, have you heard about Christoffel? No. So, it says that in mathematics and physics, the Christoffel symbols, okay, named for Erwin Bruno Christoffel. Wikipedia is wonderful this way, it gives you all these little things. So, they are numerical arrays of real numbers that describe in coordinates the effects of parallel transport in curved surfaces. Has that got something to do with robotics? And more generally manifolds. Okay. So, as such they are coordinate space expressions for the Levi-Civita connections derived from the metric tensor. Okay. And in broader sense, the connection coefficients of an arbitrary, not necessarily metric affine connection in a coordinate basis, okay, they are called Christoffel symbols. So, very simple, right, explanation of it. So, it does not matter, okay. So, that is why I have written, thus says Wikipedia, it is like almost like written in Latin or Greek as far as we are concerned. So, there are the couple of things to be understood here. One is that we do not know enough mathematics, right. So, this is 1900, so it is at least 100 years old, and you understand the era, okay, that is roughly before theory of relativity, when people were studying what happens when you have surfaces and manifolds and there is time derivative and there is space and they are combined together. So, all of this evolved in those eras, okay. And so, now there is new push to try and find out what exactly is the mathematics of these systems. So, it is not easy, okay. So, now what happens here is, anyway, so it is just that even doing this dynamics you will end up with these complicated issues which are there. So, see, we are looking at Cij Qj dot which is equal to Hij k Q dot k Q dot j, and if you replace Hij k, so we just had an expression here. So, I am just taking this term and I am putting it back in here. Now, this I split into two parts. So, there is a half here and this is 1. So, I write it as half of this and the other half I put in here, okay, except see del Bij del Qk, right. So, I write it as Bij upon del Qk into Qk dot, and this I am writing as Ik into Qj, and I am just changing the subscripts along. So, I am allowed to do that because I am summing it, okay, that you have known for few years. So, if you do that you basically get these two halves outside and the same summation sign outside. So, you just move it back inside the summation sign and you get this term del Bij del Qk, del Bik del Qj and del Bjk del Qi. Now, this thing is inside the bracket is known as Christoffel symbol of the first type, okay. So, this essentially gives you some expression of how, so when you have surfaces in space and then there is a time factor which is in there, that also somewhere you have heard, right, it warps surfaces and things like that if you have a geometrical representative. So, the same equations turned up in the dynamics of robotic manipulators, okay. So, this is just to make you feel that it is really well, it's known for 100 years, but then it's a little bit more math and a little bit more interpretation beyond what you have done so far. So that's why it's a final year course, it's a advanced course, and then you get PG courses. But this is known. So when people, this turned up in manipulator dynamics in the 70s, people were like, aha, okay. So it's the same Christoffel symbols. So what is interesting there? So Cijk is equal to Cikj, okay, and then you define this matrix N, okay, as B dot Q minus 2C Q Q dot. This is a definition. Now you have to compute B dot Q, okay, and you obviously have to compute C. So you can form this matrix. Now this matrix is Q symmetric for this choice of C. If you choose make C based on this definition, then this matrix B dot Q minus 2C Q Q dot is Q symmetric. What does Q symmetry mean? Transpose the negative of that, okay. So I will first get you down here is that the implication is that if you have made programming errors or if you have made errors in indices, then you have formed, so you can just check at the end of it, is B dot Q minus 2C, is that actually skew symmetric? If it is not, that means you have messed up an index somewhere in your programming or in your derivation. So it's a very powerful check. It's highly improbable that these matrices which are n by n will come out perfectly skew symmetric if you have made errors in either the programming or in the derivation. So it's a powerful check of your formulation and your coordination. And skew symmetry also implies that for any W, W transpose n Q Q Q dot W is equal to 0. That is the property of skew symmetry. Any vector you multiply by the matrix pre and post, it will turn out to be 0 because of skew symmetry, okay. So essentially it means that if I also, instead of, since it is true for any vector, if I multiply this by Q dot transpose and post pre by Q dot transpose and post by Q dot, then that will also be equal to 0, okay. So what Hamilton showed is that this is essentially the principle of conservation of energy, and that this is true for any C matrix that you form, not necessarily the one going through the Christoffel symbol route, okay. However, it is skew symmetric, exactly skew symmetric only if you use the Christoffel symbol route. So this is an added verification. If you choose that, okay, I will not use Christoffel symbol, then you can check finally using this, is this working out right? Okay, it's working out right. So then that is correct, okay. So this is again an additional check and essentially tells you that total time derivative of kinetic energy is balanced by the power generated by all the forces acting on the manipulator joints. So it's basically a fundamental statement and it ends up expressing itself in this form. So there are checks, like I said, there are errors, but then once you run it, you actually develop the matrices, you examine it, take a printout, look at it. There is also a test for skew symmetry, so you can test it. You find out something is wrong, means you go back and check and you will figure out what's wrong there somewhere. And finally, we see this is very, very messy, right? There are so many terms, there is Christoffel symbols and so there are these additional things which you can derive, fairly simple, that the kinetic energy of the link plus motor complex is linear with respect to dynamic parameters, mass, 3 components of the first moment of inertia, 6 components of the inertia tensor and moment of inertia of the rotor, okay. So essentially you can write the kinetic energy of the link plus motor complex by just multiplying it with a single vector pi I. Earlier what were we writing it as? We had these quadratic forms. So if you write it in terms of the joint vectors, these parameters, you write it in terms of q dot, then it is not linear, it is in a quadratic form. But if you write it in terms of these inertia parameters, it is linear. Similarly, the potential energy of the link plus motor complex is linear with respect to mass and 3 components of the first moment of area. Okay. So, how many total terms do you have here? Mass plus 3 and then plus 6, that is 10, and moment of inertia of the rotor 11. So, 11 parameters per joint and motor complex, and you can write it in a linear form, which is very interesting because of this effect that if it is linear, then you can estimate it. How do you estimate if it is linear? You can use a least square estimate. Least square estimate, you have heard about it? Little bit, somewhere, right? Have you used it? You must have used it. Come on.
Minimizing the second order norm.
Minimizing the second order norm of what? Yeah, you have definitely used it. So, estimate the straight line which passes through this, right? You have done this problem before? So, what are you estimating? M and C, right, where y is equal to mx plus c. Now, this you can do if you have a linear form. Okay. So, what you are essentially saying is that you can come here and then you can reduce that this essentially this model is linear with respect to dynamic parameters. So, that opens up the avenue to be able to estimate many of these parameters which are actually difficult to measure and compute, because it is difficult to set up a trifilar pendulum and estimate it, right. And then how do you do that? You cannot put it. So, essentially what you would have to do is you have to take the manipulator, lock some of the joints, and then find out what is the moment of inertia, change the configuration again, and then from that you have to back out. It is too complicated. So, what is actually done is you build the robot, you have CAD model, so you can estimate all of these terms which are here. Once you have estimated these terms, and then you just run the robot and you can find out what is the torque, what is the acceleration, what is the dynamic response, and then you can go back and you can estimate these parameters better from what your initial estimate was. You update and see whether your prediction is improved, and finally when you are happy with your prediction, you say okay, I have the models. Once you have the model, then you have a nice controller which will show you in the month of April how to do, how to design a controller for these kind of systems. Okay, so to summarize, we can derive the equations and we can pretty much do it in the Euler-Lagrange form. Lagrangian is large, but you can write it very, very systematically in terms of the DH parameters. You estimate the z's and then you derive the Jacobians, keep on multiplying. You have nice tools, Mathematica, MATLAB, just keep crunching it, crunching it, crunching it. Finally, you land up with the B matrix and the Hij components, Hij components. So, from that you go back and you can derive this nice equation which you can solve. Now, if you want to simulate this, you put it inside MATLAB, you can do Runge-Kutta, or you can write your own Runge-Kutta routine. There is a large number of solvers which can do Runge-Kutta, so it is not a problem. And then if you are worried about the accuracy of a solution, I have given you a check, right. You just check this term at any instant. You can check at any instant that whether B dot minus 2C is it skew symmetric, right. And if it is not skew symmetric, that means your model is giving you something weird, which means some terms which you have ignored in your derivations is now becoming prominent. Okay, so you need to think about it again. Okay, so I mean it's used in many ways like this. And then that you can essentially go back and show that it is linear with respect to the inertia dynamic parameters. So, there is a route to estimate these dynamic parameters, because some of them are very difficult to estimate through individual measurements. So, you form reasonable estimate of it and then you run your robot, you measure the torques and the accelerations at the joints, and there are standard algorithms which you can run and you will get better estimates, so that improves your model. So, subsequently you will have better performance. Okay. So, one of the things that robot companies will never give you is what are these dynamic parameters, because this is what has been tuned to essentially make the robot more efficient, and those saying as many of Bij and Hij terms you are trying to pull down to size. So, that is why they will never tell you what they are, unless it is R&D establishment which is interacting with you to improve the robot performance. Okay, so, this is actually quite a bit to digest, especially if you have been sitting in a non-mathematical regime for the last 2 years or 3 years. But operationally it is not so difficult. Okay, so, that is all the fun stuff I have today.